that you see here. Before I go to the tensor decompositions, I would like to say a word or two about two-dimensional case of matrix decomposition that will be very important in the future. So I would like to briefly remind you about the properties of singular value decomposition, which is the composition of a matrix, of a rectangular matrix, as a product of three matrices. U and V are unitary matrices of proper dimensions, and this capital sigma in the middle is a rectangular diagonal matrix that has non-negative numbers on the diagonal, which are called singular values, and the elements of the U and V matrices are left and right singular vectors. The important property of SVD is that if you obtain the SVD, it's very simple to get automatically the best approximation to a given matrix of a certain rank. And this is guaranteed by a theorem. So you simply truncate the singular value decomposition after a certain number of terms. And the other important stuff about this is that SVD of an arbitrary matrix can be computed at polynomial time. And that's why, as a method of compression of matrices and extracting important data from matrices, SVD is present basically in any field of science, I guess. If we move on to higher dimensional quantities, so if we move to tensors of order higher than 2, the problem is that there is no longer an equivalent of SVD that will retain all properties. You always lose some of the properties, either truncation property or the polynomial time computation. So in case of high dimensional tensors, there are several decomposition formats that you can use depending on your problem, and also different algorithms that are present in applied mathematics literature. In the present case of T3 amplitudes, I use something that is called Tucker decomposition. So as you see in equation 5, the tensor is written as this kind of projection onto a certain subspace spanned by these U vectors. So you can say that this central tensor Txyz is in a sense compressed triple amplitude excitation tensor in a space spanned by all possible combinations of the U vectors. A few remarks here, or a few notational issues. The length of the summation over x, y, and z, I will denote it by NSVD. It will be clear why in a second. This decomposition is exact if you include all possible excitations in the space. So in the limit of NSVD being equal to OV, which is the maximal size that you can get, this decomposition is exact. And also what is worth mentioning is that all the symmetries of the initial tensor are preserved. So in all couplet cluster schemes based on these decompositions, the U factors, so these factors here, they are fixed. They are fixed before the iterations. They are calculated before you start couplet cluster iterations. But the central tensor is obtained as a Txyz, is obtained as a result of couplet cluster iterations. So I have to tell you how to obtain the U tensors, U vectors, in a sort of optimal way. In the case of tensors, as I said, there is no unique way to do it. There is no full equivalent of SVD, but there are some methods. And in a reasonable scheme to do it is to proceed as follows. You take some approximately free, in this case it's from perturbation theory. You rewrite these amplitudes as a rectangular matrix. So you perform something called flattening or matricization of the tensor. So you write it as a rectangular matrix and you calculate SVD of this rectangular matrix obtained by flattening. Next, you simply take the left singular values, singular vectors, and you retain only these singular vectors that correspond to the largest singular values. So at this point, you start truncating, and it becomes approximate. So this is how the scheme is set up. Of course, because T3 is a large matrix, obtaining SVD of this matrix is a non-trivial task, and there are two methods in the literature to do it. The first one is based on p-diagonalization of the matrix. This method is very general, and formally it scales as n to the power 7th, but in practice it's closer to n to the 6th and has a small prefactor. And the second method, which is not yet published, is based on Laplace transformation of the energy denominators. The advantage of this method is that it's rigorously n to the 6th, but has a larger prefactor. So these are two alternatives. In both methods, you don't have to store T3 amplitudes in memory. You can calculate the singular vectors and singular values that correspond to the largest singular values in a targeted way. So you don't have to calculate everything. You calculate only thing that you need. And both methods are black box. So you don't need to input anything aside from convergent threshold or something like that. The critical point about the Tucker decomposition and the whole SVD methods in Kaplan-Meier theory is that the size of the SVD subspace that you need to keep a constant relative accuracy in the correlation energy scales linearly with the system size. So the size of the system is linearly related to the system size. This is not that something that can be, I guess, proven mathematically for a realistic system. This is more a numerical observation that holds at the level of T2, and also to show you that it holds at the level of T3, I will give you a simple graph. This graph is for linear alkanes, so n equal 1 is methane, n equal 2 is ethane, propane, and so forth. And this is on the horizontal axis. On the vertical axis, you see the size of the SVD subspace that you need to obtain 99.9% of the CC3, in this case, correlation energy. So as you can see, the size of the SVD subspace very quickly becomes linearly related to the system size. So in this case, the system size is just the length of the chain. So the number of carbon atoms. So going back to CCSDT now, how we can exploit that to reduce the scaling of CCSDT. So in ordinary CCSDT, in each iteration, you evaluate something that's called residual vector or something like that. This is equation 8. But in the compressed variant of CCSDT, you don't need that. Instead of the full residual vector, you only need a residual vector restricted to the SVD subspace. So equation 9 is the thing that you need to update the amplitudes, because as I said, these U tensors are fixed. They are plain up front, and they are no longer changed during the iteration. So during the iterations, you only need to calculate this compressed tensor Rxyz. So this is one important point. The second important point that you have to use to reduce the scaling is to remember that the size of the SVD subspace scales linearly, and you have to rewrite the equations, rearrange the equations in a certain way to exploit this linear scaling. So as an example, here we have in equation 10, you have the most expensive step in CCSDT. This is the only term that involves 5 virtual amplitudes at 5 virtual orbitals at the same time. So typically for large systems, this is the most important, the most difficult step, the most expensive step. If we decompose the triple amplitudes, instead of this term, we can calculate only the term restricted to the SVD subspace. So equation 11. And if you insert the decomposition of the amplitude, so if you insert the initial Tucker formula, so equation 5, and if you rearrange that, you can decompose it into 2 steps. And if you count the indices, and remember that the size of the SVD subspace scales linearly with the system size, you can rewrite it as 2 steps, both of them scaling as n to the 6th. So this is n to the 6th. This is just an example of the one term. Of course, you have to prove that all terms can be written like that, but it can be done. And all terms in CCSDT residual can be rearranged in this form that to a form that can be calculated with n to the 6th scaling. So, so the method that is created in this way, that I will just shortly call SVD CCSDT, scales as n to the 6th. So the same scaling as CCSD, basically. So this is the point of reducing the scaling of a method by applying 2 facts: that you work in a SVD subspace and you don't need to calculate the full rank quantities. And the second thing is that the size of the SVD subspace scales linearly with the system size, which is a numerical observation. Okay, to prove that, again, these are the timings of CCSDT, SVD CCSDT. So the black curve is CCSDT. This is also for linear alkanes. So n equal 2 is ethane, n equal 3 is propane, and so forth. So this is the timing for a single iteration. And the black curve is CCSDT. It should be n to the 8th, but I managed to calculate CCSDT only up to n to the n equal 5. So this scaling is maybe not fully asymptotic. And this is compared with the scaling of SVD CCSDT. And this is again fitted. The third curve, the red curve, is the scaling that is required for determination of the SVD subspace, because I told you that this is a step that has rigorously n to the 7th scaling, but it's closer to n to the 6th in practice because it's sparsity, as you can see here. So if you compare the timings, then SVD CCSDT indeed scales as n to the 6th power, and the cost of the SVD of the CCSDT can be reduced in this way in a quite substantial way. For example, SVD CCSDT for n equal to 6 is more or less as expensive as CCSDT for n equal 4, and you can do much more with SVD CCSDT this way. The scaling of the method is important, but what's also important is to show the errors. So of course you lose some accuracy in the process. So it's important to show how much you lose. And there will be some simple examples first. So this is the error on the graph. You see on the horizontal axis, you see the size of the SVD subspace that was used in SVD CCSDT calculations. And on a vertical axis, you see the error in the correlation energy in kilojoule per mole. And this red line, horizontal red line, is 1 kilojoule per mole. So as you can see, the error of the method decreases quite quickly with the size of the SVD subspace. This is for HCCH molecule with triple zeta basis set. I can show you the same for a slightly larger system, not very large, but slightly larger, which is HNO3. And again, the graph is the same, size of the SVD subspace versus the accuracy of the method. And again, the levels of accuracy below 1 kilojoule per mole are reached reasonably quickly. And these are results for the total energies, so to speak, so total correlation energies. which are important, but relative energies are more important. So to show you the accuracy of the method for relative energies, I did calculations for boot again, which these calculations were simply rotation around the CCCC, their dihedral angle, and the rest of the geometry is fixed. And I compare, of course, as before, with the exact CCSDT method. So I compare SVD CCSDT with CCSDT. So the trans structure is corresponds to the angle of 180 degrees. This is in double zeta basis set, because in triple zeta I couldn't get the CCSDT done. So this is the scan of this potential energy surface as a function of the angle. So on the horizontal axis there is a torsional angle. On the vertical axis you see the torsional energy with respect to in relation to the trans structure. So trans structure is the energy 0 in this case. And you can see 3 dashed lines are the curves for SVD CCSDT method with 3 subspace sizes, 40, 80, and 120 as singular vectors included, compared to the maximum size of around 800. So this is just the potential energy surface compared between the methods. If you want to see the errors, so this is just the same calculations, the same system, but instead of showing the energies, the raw energies, I show the errors with respect to full CCSDT. Also for the 3 examples of 3 possible subspace sizes. This is in kilojoule per mole again. And if you increase the subspace size, you very quickly reach the accuracy of a fraction of a kilojoule per mole. So to sum up what I have shown you up to this point, the SVD CCSDT method scales as n to the 6th power of the system size. I will show you some timings later. The practical accuracy limit of this method is between 0.1 and 0.3 kilojoule per mole. Beyond that, you start seeing, first of all, some numerical noise, but the second of all, the subspace size must be quite large, and it's hard to go beyond that. If one is trying to get 1 kilojoule per mole out of the method, then the cost will be several times CCSD, more or less. And for potential energy surface, the method is quite systematic. You don't see some jumps on discontinuities, which is important for finding spectra and stuff like that. And another important thing that the method is completely black box as is implemented now. You only have to give one number to get results. So the size of the SVD subspace is the only thing that you have to provide. You typically do calculations for 2, 3, or 4, and you see whether they stabilize or not. So you don't have to specify any triple excitations by hand or any stuff like that. Everything is done automatically. And the last thing, there are no memory bottlenecks because you don't store the T3 anymore. You store only this compressed quantity that is much, much smaller than the full rank triples tensor. Okay, so this was the work that has been published already, and I will show you some things that I'm working on now. So first thing is that if you have a converged SVD CCSDT, what's the source of error? The source of error is, of course, that you have excluded some triple excitations from the SVD subspace. The SVD subspace is never full. In practice, some triple excitations are missing, and this is the source of error. So the question is, now you have a reasonably good wave function, SVD CCSDT. The question is, can you account for the missing triple amplitudes by using sort of perturbation theory or some non-iterative correction? And it turns out you can, if you apply perturbation theory in some variance that is more like equation of motion type theory, you arrive at the correction that is given by equation 14. This is a non-iterative correction. So you simply add that on top of SVD CCSDT, and this correction accounts for the missing triples that were excluded from the SVD subspace. So the general idea is is a bit similar to parenthesis T, but instead of CCSD starting wave function, you have SVD CCSDT now. So I will call this method SVD CCSDT plus, and some important properties of this method. The correction given by equation 14 can be evaluated with n to the 7th scaling. So this is non-iterative n to the 7th correction that is very similar in nature to the famous parenthesis T. And actually the implementation of the method is also very similar as in parenthesis T calculations. The prefactor is of course larger because there is much more stuff on the right hand side. I mean, there's additional terms, but the scaling is formally the same. And other two important properties of this method is that if you have no vectors, if your SVD subspace, so n SVD is equal to 0, SVD CCSDT becomes CCSD. If you have no triple excitations, then the method is simply CCSD. And in this case, the SVD CCSDT plus is approximately equal to the parenthesis T plus some terms that are quadratic in T. So they are presumably much smaller, at least for well-behaving systems. So your starting point, basically with zeros, with size of the subspace equal to 0, is basically parenthesis T. And in the converse case, which you may expect, if you have a complete SVD subspace, so you include all possible excitations in the subspace, both SVD CCSDT and SVD CCSDT plus become equal to CCSDT rigorously. So in other words, this correction given by equation 14 is 0 if you have true CCSDT wave function. So there is no overcorrecting or double counting. The limit is strictly well known. As an example, just this is the last two slides, I will give you a numerical example of isomerization energy of acetone into occitan. These calculations were done in triple zeta basis set. This is slightly above 200 basis functions. So this is in the table, you see the isomerization energy calculated with SVD CCSDT. And if you follow the numbers, you see that SVD CCSDT is converging somewhere, but you would still need to get a step or two above to fully converge it to be sure that this last number is stable with the size of the SVD subspace. But as I said before, it will be difficult to get beyond 0.1, 0.2, 0.3 kilojoule per mole. It will start to oscillate slowly. So now I will add the results of SVD CCSDT plus. So after adding this non-iterative correction that accounts for the missing triples, and in this case, if we look back to the table, the results stabilize much more quickly, and already with this SVD subspace of 120 or so, you obtain the result that is probably more accurate than 0.1 kilojoule per mole. So this correction can be used in two ways. First way is simply it's time to conclude, Michał. Yeah, I know. So the first way is to use this plus correction in the case when your SVD subspace is small, just to get a much better result out of a small SVD subspace. And the second way is really to converge to accuracy below 0.1 kilojoule per mole, which is difficult with SVD CCSDT. After the plus correction, as you can see, this can be done. The last word about timings, they are given below. The timings for, in this case, for the size of the SVD subspace equal to 120, which already gives very accurate results. The timing of SVD CCSDT is about 4 or 5 times the timing of CCSD. This includes the termination of the triple subspace. So this is the actual time you have to spend to get the number. So this is real time to solution number, and the cost of calculating the plus correction is more or less the same as the cost of the CCSD iteration. So these are the full calculations, not a single iteration. I wanted to show you something about the quadruples corrections because I'm working on them now, but I think it's time for me to end. So with this, I will thank you for your attention, and I'm looking forward to your questions. Thank you.
Thank you, Michał, for your presentation. Now it's time for questions. We allow our participants to ask the questions. Let me maybe ask the question, Monika Musiał.
Michał, thank you. Very nice talk. Do you consider to go further and, for example, include quadruples?
Yes, I'm working on parenthesis Q. Can you hear me, by the way?
Yes.
Okay, so now I'm working on parenthesis Q. I don't have an implementation ready yet. I mean parenthesis Q, by parenthesis Q, I mean the parenthesis Q of Kelly. So with
non-iterative variant, yes?
Yeah. Non-iterative variant from the papers of Kelly. And I cannot show the numbers because I don't have the implementation ready. But I have the equations ready that I'm implementing right now. And what I can tell you for certain is that it's n to the 7th. If you apply this decomposition and Laplace transform for denominators in T4, then you can calculate parenthesis Q n to the 7th.
Michał, you have a question from the participant, Marcin Goronowski. His question is the method consistent in size? Well,
the method is not rigorously size consistent in the sense that you enforce size consistency by increasing the subspace size. This is the best answer. So I guess.
Further questions? Has anybody further questions? If not, thank you, Michał. Okay, so let me, there are in fact 2 questions. Anastasia, what is the practical size of the system you can treat? Can you go to few tens of electrons?
Yes.
Okay, what is the practical size of the system? I mean, then what is the maximal size? I mean,
well, it of course depends on the basis set. In the case of double zeta,
and try to answer in compact way.
Yes, in the case of double zeta, the calculations, the larger calculations that I did was for alkanes with n equal 12. So okay. C12H something.
Michał, another question from Philip Hogan. What Laplace transform algorithm do you use for denominators? On the graph are n 614 up to n 645 in the right order.
Sorry, I must have misheard you.
See the chat. Open the chat. But let me say that everybody can now unmute themselves and ask questions directly. So
okay,
if you have any questions, you can unmute and ask the question now.
I use for Laplace transform, I use min-max quadrature of Hack-Bush and Tenno.
Okay. So are there any further questions? Michał has a question.
Yes, the graph, it's not clear from the numbers whether the scaling n to the power 6.14 and n to the power 6.44.
It looks like a mistake.
Are they the right way round?
Michał Lesiuk, maybe you can, because it is not the right order. So
is it the right order or not? It may be because the bottom curve is very small.
The bottom curve simply has a smaller prefactor.
Yes.
The order is the same. So it should be, that's why it's proportional to.
Yes.
But
so
simply the prefactor is larger in the lower curve.
Okay, that's quite possible. Thank you very much. Nice talk.
Thank you very much.
Okay, so you said that SVD subspace for triples, scales linearly, and this is just numerical observations.
Yes.
And is there any physical insight why it should be like this? That relevant part of the SVD subspace is linearly proportional?
I work on it, trying to show something for spin systems or Hubble models, but nothing to write home about yet. So I can answer, work in progress, I guess.
Okay, are there any further questions? If not, let Michał, we are thank you again. You can unshare the screen. Okay, you can also mute yourself. And now we are